My name is Tucker Vento. I'm an AI team lead, or engineering team lead. I'm not an AI yet. I'm an engineering team lead at Bloomberg.
My name is Yifan. I'm a software engineer on Tucker's team.
Yeah, together we're on the AI training and notebooks team. We're going to focus on the latter half of that today, talking about how we secure and scale wow, it's going to be long. Jupyter at Bloomberg. So quick agenda. We're going to start by describing the AI infrastructure in general at Bloomberg. We're going to take a quick look at some key Kubernetes concepts, something you'll need to understand how we built our platform. Then Yifan will walk through the Jupyter Notebook platform itself and how we secure and protect the user workloads inside of it. We'll discuss some of the enhancements we've made to the developer workflow, as well as some of our own challenges we faced in running this platform. And finally, some of our future plans for how we might improve it. So what is this platform? Well, we're very creative with our naming, so we named it the Data Science Platform. It's the foundation of AI at Bloomberg for all things large-scale computation, machine learning, data science. It's a multi-cluster and multi-tenant system built on top of Kubernetes, and it's designed to support diverse workloads across multi-region teams. It provides a complete MLOps experience, from data exploration and model training to fine-tuning, versioning, and deployment of inference services, all powered by state-of-the-art compute and GPUs. And it relies on a very powerful ecosystem of open source technologies, including Jupyter for data science and exploration, Kubeflow and Ray for training, Kser for inference, Karmata for multi-cluster orchestration, and many others. But we're focused on one part today. We're focused on the notebooks. So before we dive into that, though, we got to talk about Kubernetes, because without it, we would have nothing. So Kubernetes is an open source system for managing and deploying containerized applications on a large cluster of machines. Containerized applications are lightweight bundles of everything that application needs to run, its code, its libraries, its configuration, so it behaves the same way no matter where you deploy it. We can think of Kubernetes like a big distributed state machine. You tell it what you want the world to look like, and it's going to take continuous action on your cluster to bring the state of the world to that state. A self-healing distributed control loop of sorts. Now, one of the smallest building blocks we have is a node. It's the machine, it's part of your cluster. It's where your notebooks and your pods run. But what is a pod? Well, a pod is the smallest deployable unit in Kubernetes. It's a cluster of, I'm going to overuse that word. It's a group of containers that are managed, scheduled, and ran together. They have a shared environment, the same network, same IP. They might share volumes. There's very tight coupling on their lifecycle. They're going to run together. They're going to end together. This provides an easy point for us to extend on. We can build sidecars or processes that know about these pods and talk to the containers inside of them. But these pods are ephemeral. Kubernetes is based on stateless design principles, so these pods may disappear and restart at any time. And we're going to have higher level constructs that help manage that. One of those higher level constructs is a service. So it's a little bit above a pod, and it's give us a stable entry point to find pods. It'd be really annoying if I had to remember all the IPs of the pods I want to talk to. So instead, I just know the name of the service. And it provides service discovery, so it can automatically load balance and send my request to where it needs to go. And this provides us good decoupling. Client doesn't have to worry about the pods, just the service that it needs to talk to. If we zoom up again, we get namespaces. Now, namespace is just kind of a way to provide isolation, organization, and scoping for the resources in our cluster. It's how we start to provide multi-tenant concepts into our platform. We can have different access rules or different resource quotas assigned to different namespaces. It's a logical partition that's going to group the related pods and services while also providing isolation from other namespaces in the cluster. So everything we've talked about so far are called resources. Kubernetes has a lot of them. But it also gives you an easy point of extension by letting you define custom resources, or CRDs. So you can teach the cluster to understand and manage new types of objects beyond the built-ins like pods and services. We call an instance of a CRD a custom resource, or a CR, and one of our types of CRs is a Jupyter notebook. And it's meant to manage the entire lifecycle of a notebook on our platform. Now, once created, a custom resource is going to behave just like a native resource. It's going to get watched by custom controllers for reconciliation and management within the cluster. A controller is the control loop that helps to make up this distributed state machine. So for every resource, there is an associated controller, and it supports the declarative model of Kubernetes. It allows us to say, here's the thing I want, and the controller figures out how to get it to where you want it to be. So for our custom resources, we need to build custom controllers to help manage them. And everything that Yifan's about to describe builds on top of all of the built-in types we've described, as well as more complex custom resources provided by different open source projects and that we've developed in-house.
Thanks, Tucker. So now let's get back to our Jupyter Notebook platform at Bloomberg. So our infrastructure runs on CPU and GPU worker nodes, which was managed by Kubernetes to provide a container orchestration system. So on top of that, we integrate a bunch of open source components. For example, we have Istio for service mesh. We use Calico for notebook egress network control. We use Open Policy Agent, OPA, for ingress authorization. and we use NVIDIA device plugin to enable GPU in our notebook containers, and we use Kubernetes secret store CSI driver for secure credential injection. So we also have supporting systems such as like the log, metric, and event collection system. We also have the metadata synchronization system to help us connect to other Bloomberg services. And at the application layer, we built a bunch of CRDs and controllers, including the Hadoop and object storage identities. And we have this Jupyter Notebook controller, which manages the lifecycle and orchestration of Jupyter Notebook custom resources across the platform. So you might be wondering what happens when we launch a notebook in our cluster. So this whole process is started by creating a Jupyter Notebook resource, custom resource in this Kubernetes cluster. So we use Kubernetes namespaces to isolate the resources of different tenants. So in this example, you can see that this notebook is created in the AI LLM namespace. And on the left, you can see a minimum example of the Jupyter Notebook resource. So when the notebook resource is created in the cluster, the Jupyter Notebook controller watches on the creation event of such notebook resources and starts to reconcile the notebook resource. So the reconcile loop creates an Istio virtual service and a Kubernetes cluster IP service, which are both part of the ingress control process. And it also creates a notebook pod where the Jupyter server and the kernel is actually running. So in the notebook definition, you can see that we set the size to GPU small, which will cause the resulting notebook pod to ask for 1 GPU resource. So Kubernetes will be responsible for scheduling that notebook pod to a node with free GPU to run that notebook container.
So notebook instance is up and running. We get a link to open it in our browser, but what actually happens when we click on that link? First, we need to check that you are who you say you are, and you're actually allowed to see the thing that you're trying to see. We can think of it like when you're entering a multi-tenant office building. First, they check your ID at the door. That's the authentication. And then when you try to go to your office floor, you might need to swipe again to get in. That's the authorization. So together, authentication and authorization create the ingress control layer that helps protect the workloads inside of our system.
So our authentication system is built on Bloomberg's internal single sign-on system. So when a user first opens the URL of a Jupyter Notebook, the request first arrives at an Istio gateway. The gateway forwards the request to an Istio virtual service, which was previously created by the Jupyter Notebook controller. This virtual service further routes the traffic to another component called network proxy. The network proxy receives the request and performs an initial check of a valid token included in that request. And if this request lacks such a valid token, it would redirect the user to the Bloomberg's internal single sign-on login page. The user needs to enter their username and password in the login page, and upon a successful login, the SSO provider would issue a JWT token, including the user's identity, and send it back to the network proxy component for final validation. And the network proxy forwards the authenticated request to the notebook pod through this cluster IP service, which was also created by the notebook controller. And inside the notebook pod, the request first reaches this Istio container, sidecar container, instead of the actual container that runs the notebook. So in this Istio sidecar container, it enforces an additional layer of authentication by checking if this token exists in the authorization header, and if it does have this bearer prefix. And also, it needs to verify that it is issued in the Bloomberg.com domain. So after the request is successfully authorized, the next step is authorization. To achieve this, we use an Istio external authorization envoy filter, so which it delegates the decision to an OPA server. An OPA we talked about before, it's short for Open Policy Agent. It's an open source general purpose policy engine. So first, this Istio sidecar forwards the authenticated request to the OPA server. The OPA server periodically downloads OPA bundles from an external service called OPA Bundler. Each OPA bundle consists of 2 parts. One is a JSON file that includes the actual authorization rules, and it has a code script that describes how to evaluate the request against those rules. So this is one example on the right. You can see from a JSON authorization policy file. So this item basically tells us that the user called LDAP user Yifan is allowed to perform the access action on any resource in the AI-LLM namespace in the notebook cluster. Yeah. So inside the Opus server, it runs the code in the bottom right corner against the incoming request, and if the request successfully passes the authorization check, the Istio sidecar container would allow the user's request to finally reach its destination, which is the notebook container in the same pod. So these steps make sure that only authenticated and authorized Bloomberg users are allowed to access the notebooks running in our platform.
So ingress is how we get into the building, but once you're inside, you probably want to talk to something outside. Very few of us can do data science with all this stuff in our head. So how do we give you access to all the APIs and databases and services you need without accidentally giving you access to our entire production network? We don't want you to be able to connect to systems that you shouldn't, whether it's accidentally or intentionally.
So we use Calico network policies to restrict the notebook egress traffic to individually allow access to specific services and machines that support our engineers and data scientists. So we start by defining a Calico global network set in the bottom left corner. So this Calico network global network set, it has a special annotation that matches all the machines that run Bloomberg's internal S3-like object storage service. So these annotations depend on an in-house CIDR resolver that watches the machine groups, resolve these CIDR blocks, and associate with those machines that run the service, and populates the net field of this global network set. So this ensures that Calico has an up-to-date list of all the addresses of those machines, no matter how large or dynamic that pool of hosts may be. So once the network set is defined, we attach a Calico global network policy to it on the top left corner. So this policy basically tells us that, first, it allows any outgoing traffic to the port 443 of any machine running the object storage service, and it by default denies any other outgoing traffic. So the Calico global network set and global network policies are stored in the Kubernetes cluster, and they are watched by the Calico controller running on the master node, just like our notebook controller watches on the Jupyter notebook resources. So the Calico node worker pod throughout our cluster translates the policies they receive from the controller into IP table rules and writes them directly to the IP table of the nodes where they're running. And as a result, any outbound connection attempt from a notebook to a service that is not explicitly allowed will be rejected right at the kernel level before they can even leave the worker node. So this ensures that notebooks can connect to only pre-approved external services, and they cannot reach any arbitrary destinations in our production environment.
So we've covered the ingress and the egress, getting into and out of the platform, but once we're inside, we do need to actually do some work. And so we've tried to make some steps to ease the developer experience and help them in their day-to-day work. Yifan?
Yeah, so one of the efforts we made is Git credential injection. The goal is to provide our notebook users with automated access to internal version control system. So we achieved this by utilizing the Kubernetes secret store CSI driver, which is a special mechanism to enable secrets stored in external services to be mounted as files into the containers running in the Kubernetes cluster. So here is how it works. So on the bottom right corner, you can see that we store users' long-lived Git credentials in Bloomberg's secret management system. And we also developed a component called BB Secret Store CSI provider, which knows how to talk to the secret management system and how to fetch secrets from it. So when a new notebook resource is created, we automatically create another resource named a secret provider class, which basically tells the CSI driver which provider I would like to use and which secret I would like to fetch from the external secret management system. So the platform automatically selects the Git credential of the creator of the notebook so that nobody else's credential will be used into this notebook. So in the pod spec, we reference this secret provider class by defining a new CSI volume section. So this CSI volume references the secret provider class, and when this pod is created, the CSI driver sees this CSI volume field on the pod spec. So it talks to the corresponding provider asking for this credential. So once it receives the credential from this provider, it mounts it as a file to the Kubernetes, to this notebook pod running in the cluster as a file. So inside the notebook container, there is an init script which reads the content from this file and configures Git automatically, so that when user runs git pull and git push, it just works. So all of this happens transparently to the user. It is secure and automated, and gives every notebook instance out of the box Git access. And another enhancement we made was to allow notebook users to securely and effortlessly connect to company-wide storage solutions, for example, HDFS and object storage. So we achieved it by using a combination of CRDs and secrets to configure, define, and inject those storage connection credentials into notebook pods. So let's take object storage as an example. So we introduced a Kubernetes custom resource called Object Storage Identity. Each object storage identity resource owns a Kubernetes secret, which holds the sensitive authentication information required to talk to the object storage service. For example, the secret key and access key. When a user creates a notebook, they can specify which storage identity they would like to use in their notebook. In this case, it's the LLM dataset bucket identity on the top left corner. So this information is automatically translated into an annotation on the resulting notebook pod. The object storage identity controller watches for the creation of those pods that carry such special annotations. When such a pod appears, the controller injects the corresponding credentials into the notebook pod's environment variable by pulling them from the secret owned by the associated object storage identity resource. And as a result, when the notebook starts, it already has all the necessary credentials available as environment variables to talk to the object storage service.
Great. So we've seen what the platform looks like, how we secure it, and how we make their day-to-day work smooth, and you all have seen that Kubernetes is just YAML. So by building the platform, we've only really done half the job. The rest comes when we maintain it. How do we keep it secure when things break, when we need to scale, when the requirements change? So I'm going to share a few stories about the operational challenges and the silly lessons we've learned on keeping the platform reliable. So the first one is a zombie apocalypse. We got alerts that zombie processes were piling up on our machines. Hundreds, even thousands of them. Why is this a problem? Well, Linux has limited process space. There is a future in which we could run out of processes and users would no longer be able to spawn new ones. And we can't just kill the processes because these are owned by the Jupyter notebooks. Users are actually doing things. This was happening across namespaces, across users. It seemed like a platform problem, not a user problem. So we did a lot of careful investigation, and by that I mean Yifan did a lot of careful investigation. And we found the problem was very simple. It was these 4 characters. So in our startup script, where we start Jupyter Lab, we used exec. And if you're familiar with shell scripting, you know that exec replaces your current process with a new process. It doesn't spawn it, it actually replaces it. And that's a problem because Jupyter is very smart, but only about some things. It doesn't know how to manage Linux processes. So as the kernel would spawn child processes, and as they would die, the parent never came to pick them up from school, and they were stuck. So the fix was we deleted those 4 characters, and everything was fine. Next problem, user came to us, they say, hey, I saw my S3 credentials in the startup logs for my notebook. That's not good, because what if someone else saw those logs? Not great. So we did some testing and we realized this was only happening in certain cases, only if they were using a certain S3 content manager, which required that the argument or the credentials be passed in as command line arguments. So once again, we did some careful investigation, and it was again in the startup shell script. We provided the credentials and the arguments as was required, but we had this devious little line at the top where we set -x. Again, if you're familiar with Linux shell scripting, you know that this turns on debug logging. So every command you write prints out the standard out. This is very helpful when you're developing a shell script. This is very bad when you productionize it. So again, the fix was simple. We deleted those 6 characters. We also did a little bit more because this is a little bit more sensitive. We implemented a fluent bit filter. This is another open source tool that we put in between our containers and the logging system we use, which I think is now actually called Falcon Log Scale, but Humio is a cuter name. So this way, even if a user didn't have our update, their secrets wouldn't appear in plain text again. Now, these 2 stories are good reminders that no matter how big and complex a distributed system you build, your shell scripts are still the reason it breaks. So those small script details can cascade into larger operational challenges, and your security risks don't always come from very complex bugs. So the last one isn't really a bug, but more just an enhancement. Used to be our users would have to select a cluster to run their notebook on. And why is this a problem? Well, it made our users very sensitive to the infrastructure changes. If we had to bring a cluster down, oh, they can no longer pick that cluster. They might be alarmed, like, why is my favorite cluster gone? Or their notebook is stuck there and they need to move it over manually. This is really annoying for a user. So we wanted to abstract it all away because it also led to uneven hardware utilization. It turns out the first cluster in the drop-down list is the only one they pick. So they weren't really doing a good job of spreading their load around. So we had to add an abstraction layer. And this is one slide, but it took months of work, so we should probably do a talk on it. And actually, we are doing a talk on it at KubeCon next week. So if you know anyone that's going to be there, go check it out. But we added this thing called Karmata. It's an open source Kubernetes federation system so that users submit their request, and Karmata helps decide which cluster has enough resources and is healthy enough to service that request. So they no longer care about where their workload runs. We handle all that for them, and we get much better resource utilization as a result. So finally, I want to cover some of the things we want to talk about, or one of the things we want to develop in the future, and some of the things we might be talking about next year at JupyterCon. One of them, this is not one of them because it's pretty much just NFS, but it can't be NFS for reasons that I'm not going to get into right now. But we want to add a distributed file system because right now all of our notebooks only have access to local ephemeral storage. If your notebook dies, you better have used S3 or HDFS or GitHub to persist your work. We want to add a distributed file system that all clusters can rely on. Which would give better sharing, persistence, and recovery of data. Again, if this looks like NFS, that's because it should be, but it can't be. So this one's a little more interesting. We want to separate the server and the kernel. Right now, these things run together in the same pod. They're in the same set of containers. But this means that there is tight coupling, remember. So if that Python kernel dies, there's a good chance the Jupyter server is going to die as well. That means you lost your work. That stinks. So we want to separate the two. We can run the kernel anywhere we want. And if it dies, you're fine. Your server's still there. This would also allow you to change your kernel on the fly. Right now, when a user submits a notebook request, they need to tell us how many GPUs do they want, how many CPUs, all that sort of stuff. They could start with a small CPU workload and then decide, you know what, I need an H100 now, and they can go and do that. So it's going to give them a lot more dynamic job capabilities and hopefully give us better resource utilization as a result. So hopefully you'll see us next year talking about this, and we'll contribute it back upstream. And that's all we've got. So hopefully we have a little bit of time for questions. We are hiring, so please check that link. And we also have a really cool PhD fellowship that has a very long URL, so please take a picture of it, or just search Bloomberg PhD fellowship in your favorite search engine. You'll probably find it. Thank you.